The technology world has been sent reeling by Apple's unexpected unveiling of a revolutionary artificial intelligence architecture that delivers unprecedented 85-fold performance improvements over current industry standards, effectively leapfrogging every major competitor in one stunning announcement that fundamentally rewrites the rules of what's possible in edge computing and neural processing. Dubbed Apple Neural Engine 2, ANE2, this breakthrough isn't merely an incremental upgrade, but a complete reimagining of how AI computations are handled at the hardware level, combining a novel 3D stacked chip design with what Apple is calling sparse attention processing, a technique that dramatically reduces computational overhead by focusing only on relevant data pathways rather than processing entire neural networks uniformly. This architectural marvel achieves its astonishing speed advantages through multiple innovations working in concert. A photonic interconnect layer that allows near-instant communication between processing cores using light rather than electricity, eliminating the data transfer bottlenecks that plague conventional AI chips. Memory on processing architecture that embeds specialized SRAM directly onto each compute core, reducing memory access latency by 97%. And a dynamic precision adjustment system that automatically varies numerical precision throughout computations, applying high precision only where absolutely necessary, while using ultra-efficient lower precision for less critical operations. The result is an AI system that can run models like GPT-4-level large language models directly on device at conversational speeds without any cloud dependency, while consuming 92% less power than current mobile AI chips. A combination of performance and efficiency that seemed physically impossible just months ago. What makes this development particularly shocking to the industry is how completely it bypasses the conventional trajectory of AI hardware development. While competitors were focused on packing more transistors into smaller spaces and developing increasingly complex multi-chip modules, Apple's approach fundamentally rethought the physics of computation itself. The ANE2's photonic computing elements use silicon photonics to perform matrix multiplications, the core operation in neural networks, at the speed of light, with minimal heat generation and power consumption. This is complemented by a reconfigurable dataflow architecture that can dynamically reorganize its computational pathways to match the exact requirements of whatever model is running, whether it's computer vision, natural language processing, or audio analysis. A flexibility that eliminates the inefficiencies of fixed-function hardware accelerators. Perhaps most impressively, the system includes on-chip learning capabilities that allow devices to continuously improve AI models based on user interactions without compromising privacy or requiring cloud connectivity, using a novel federated learning implementation that operates entirely locally while still achieving results comparable to cloud-based training. Early benchmarks show the ANE2 processing 23.8 trillion operations per second while drawing less than 5 watts of power. Performance that not only dwarfs mobile competitors, but surpasses many desktop AI accelerators while consuming a fraction of the energy. The implications of this technology extend far faster smartphones or more responsive voice assistants. Apple's breakthrough enables applications that were previously confined to science fiction. Real-time high-fidelity augmented reality becomes suddenly practical, with the ANE2 capable of processing spatial mapping, object recognition, and physics simulation simultaneously, while maintaining impossibly low latency. Professional-grade creative applications like video editing and 3D rendering can now run with AI-assisted features directly on mobile devices, eliminating the need for cloud processing or powerful workstations. The healthcare sector stands to be transformed through always-on health monitoring that can analyze medical sensor data in real time to detect anomalies and predict health events before they become critical, all while maintaining complete data privacy on the device. Even autonomous systems benefit dramatically, with the technology enabling real-time decision-making in robots and vehicles without latency concerns, potentially accelerating the development of fully autonomous systems that can operate reliably without constant cloud connectivity. Apple achieved this astonishing leap through a multi-year secret initiative that combined expertise from their acquisitions of AI startups, semiconductor specialists, and even materials science researchers working on advanced photonics. The development process reportedly involved completely new design tools and simulation software, as conventional electronic design automation tools were inadequate for modeling the photonic components and 3D integration. Manufacturing the ANE2 requires groundbreaking fabrication techniques, including monolithic 3D integration that builds processing layers directly atop each other rather than packaging separate chips, and extreme ultraviolet lithography at resolutions previously only achievable in laboratory settings. Industry analysts suggest Apple's vertical integration, controlling everything from chip design to operating system to development tools, gave them the unique ability to co-design hardware and software in ways that competitors fragmented across different companies simply cannot match. This tight integration allows features like MLX Enhanced, a new version of Apple's machine learning framework that automatically optimizes models to take full advantage of the ANE2's unique capabilities without requiring developers to have specialized knowledge of the underlying hardware. The competitive landscape has been completely upended by this announcement. Companies that were competing on marginal improvements in traditional AI accelerators now find their roadmaps obsolete, while cloud providers who built businesses around offering AI as a service must suddenly contend with the possibility that most AI processing could shift to devices. Apple's timing is particularly devastating to competitors who had been planning their own next-generation AI chip announcements for later this year, now forced to either delay launches for complete redesigns or proceed with products that are suddenly generations behind. The environmental implications are equally significant. By enabling complex AI processing on devices rather than in energy-hungry data centers, Apple's technology could potentially reduce the carbon footprint of the AI industry by millions of tons annually as cloud inference workloads shift to edge devices. Perhaps most intriguing are the longer-term implications for artificial intelligence development itself. With such massive computational resources available locally, the fundamental economics of AI training and deployment may shift away from the centralized cloud model that has dominated the field. Researchers could experiment with novel architectures without incurring massive cloud computing bills, while consumers could benefit from truly personalized AI that learns from their behavior without privacy concerns. The ability to run large models on device also addresses one of the most significant limitations of current AI systems: latency, enabling applications that require instantaneous response, from real-time translation to interactive educational tools that adapt to student understanding moment by moment. As the industry struggles to comprehend how Apple achieved such a dramatic leap, attention is turning to how quickly competitors can respond and what the second-order effects will be across the technology ecosystem. One thing is certain: the rules of AI hardware have been rewritten overnight, and the company that seemed to be playing catch-up in artificial intelligence has suddenly established a lead that may take years for others to match. In typical Apple fashion, they didn't just improve existing technology, they redefined what was possible, and in doing so, have likely shaped the next decade of computing. The shockwaves from this announcement will reverberate far beyond Cupertino, affecting everything from semiconductor manufacturing to cloud infrastructure investments to the very nature of how we interact with intelligent systems in our daily lives.